Hello, it's Eugen. In this short video I will tell you how to get constant high voltage, for example 900 volts DC, or it may be bipolar plus minus 450 volts from the standard grid voltage. It may be 220 volts as we have in Russia, or 127 volts alternating current to charge high capacity electrolytic capacitors. Okay, let's go.
At first, I would like to say a couple of words about why this question arose. In my new multi-stage electromagnetic accelerator, I used grid power supply from standard alternating current network. It is 220 volts in Russia. And an idea came to raise voltage and to increase power supply voltage on capacitors. The problem is that standard electrolytic capacitors has maximum voltage of 450 volts, as you can see. There are some models of 500 volts, and maybe I'm sure that some special models have much higher voltage, but it is not freely accessible. So, if I want to increase voltage more than 450 volts, I need to connect such banks in series. So, two connected capacitors of 450 volts give us 900 volts, and accordingly we should have some charging circuit for each stage of such cascades of capacitors for a multi-stage accelerator. Let's look how can we get it.
Okay, so we have standard grid outlet. It is 220 volts, or it may be 127 volts alternating. And the easiest method to obtain constant DC high voltage is to get high voltage transformer. It is not a very widely spread thing, but it can be obtained. So now in the secondary circuit we have controlling switch, then diode. It may be a simple diode or a bridge. The bridge will be connected in another way. I will not write it down here. Switch may be placed here and here, and then we place in series our capacitors, 2 or 3 or whichever we get. Here is the polarity of these capacitors. Okay, and they are charged. To get 900 volts DC, we should have according amplitude in the secondary. It must be more than 900. So, what is the minuses of this circuit? The capacitance of these caps is not equal, so when they are charged, to avoid overcharging, we must set flattening circuits. They consist of simple powerful resistors or Zener diodes or stabilitrons as they called in series. So they function as follows: when the voltage over the capacitors exceeds some limit, zeros are open, the current begin to flow through the circuits. So the disadvantage is that very high power losses here. And so if we try to charge not a single block of such capacitors, but for example coil gun with many stages, we must obtain all this, we must provide all these blocks with according circuits, and it is very complicated structure we have. Very complicated and very inefficient, because losses of heat are very high in each stage. So what should we do? Let's use two secondary windings. And we will talk later how to construct such a circuit. Now we have switch, rectifier in each branch. These windings should be connected in series, and in the lower branch we also have switch and rectifier. It works backwards, so we have negative voltage in this branch, and intermediate point is also layout. Here are the secondary capacitors in which we will monitor the voltage in both branches, and the charged electrolytics are connected in such a manner with connection to the medium point. Here is the polarity, and I forgot to write a second diode. Okay, now we have two independently charged branches with a medium point which can be connected to the ground of the whole circuit. So we don't need any aligning circuits now, because the charging of these capacitors is independent, with two sources which are controlled through these rectifiers and these two switches. We have no flattening circuits, no heat losses. And so if we want to charge another bank, we connect it in such a manner. Here is the polarity, and the negative branch is here. So it's fully analogous to the first cascade. It also doesn't need any flattening circuits and doesn't lead to any losses. Here is the third cascade, and so on. This circuit is very handy because it is much more compact, and it has a medium point in regard to which we can measure voltage. It is very handy, and we'll show how to manage it with simple operational amplifiers or comparators. To realize the circuit above, we should have one transformer with two windings, step up, but I didn't have such a transformer, so I used two simple anodic transformers, TA30 and TA1. They are very widely spread, can be easily obtained. So they can work with 127 and 220 volts both grid. This connection, which is shown here on this picture, is for 220 volts. To use it for 127, you should reconnect the primary winding in a way which is shown in the corresponding datasheet. Okay. For 220 volts, pins 2 and 6 are connected in series, and the phase voltage is applied to the pins 1 and 8 of the primary winding. Okay. Now, we take the first phase wire and connect it to the ground of the circuit. It is not very safe solution, but it allows us to do some trick, which I will tell you now. And the second wire is connected to the primary windings of the transformers, and also it is connected to the secondary winding of the TA1 transformer. In secondary winding we begin to collect voltages and in plus to the initial voltage, grid voltage. Okay, on the first secondary we obtain 28 volts, 12th and 13th is connected. In the second we also have 28. Then we on the third secondary winding and fourth we also have 28 volts. So on this transformer we have 4 times 28 volts. Then we connect it to the first transformer TA30, and we also get 2 secondary windings of it, and on the outlet wire we obtain 220 volts of initial AC and 6 times 28. So it gives us 388 volts AC, which when rectified, gives us about 550 volts in plus and minus in regard to the ground. So it is much more than enough to charge our electrolytics to 450 volts. So low voltage secondary windings also are usefully utilized here. We get them in series and obtain 12 volts alternating current. It can be easily rectified and used for some linear circuits in our scheme. This table explains why I used these transformers in such a way. TA30 has much more powerful secondary windings. They give us 460 milliamperes, and in TA1 it is only 148 milliamperes. So this circuit is much more powerful. Okay, what can we do with 388 volt AC? How can we get the told above 2 shoulders to charge? Very simply, we divided this voltage into 2 branches. This is negative and this is positive branch. They have rectifying diodes, these 2 diodes. This is a ballast resistor to reduce pulsations. These are controlling switches. I used opto-relays to realize these switches. They have maximum rated voltage of 600 volts. It is much more than enough for us. Through these relays, these shunting capacitors are charged. I used little electrolytics for this purpose. They are 450 volts and 10 microfarads. Voltage of them is monitored through these dividers with trimmers, so it may be trimmed, and the control voltage is fed to the input of the operational amplifiers. It may be LM158 or LM324 or another common operational amplifier. This alternating voltage is rectified 12 volts, and through linear regulator is fed directly to the input of the circuit. It gives us 9 volts stabilized voltage for some further circuits maybe. And this divider gives us, I used 5 and 1 volt Zener, so it is in the medium point of these operational amplifiers in their working range. And this 9 volts also is fed to the operational amplifiers as power supply. This circuit works simple when the control voltage exceeds the set value. Operational amplifier closes the relays and charging stops in both branches. So the only difference is that the amplifiers connected in a different way. One is inverting and other is non-inverting. Very simple circuit. It can be also made with comparators, but I used amplifiers. So what we have? We have plus 550 volts DC and minus. So we have plus minus 450 volts, as I said. Intermediate point, ground. Also we have 9 volts stabilized and reference voltage of about 5 volts. Okay, now I'll show you how it is realized in iron.
Okay, this is a part of my accelerating stand which realizes the principles told above. Here are our two anode transformers. You see one of them, it is TA1, so this is J30. These are ballast resistors, and here is a self-made PCB with you can see two octapairs which are controlling switches. Here is operational amplifier. Here blue are trimmers which regulate voltage in negative and positive branch. Here are also some auxiliary diodes which ignites when the voltage on capacitors is close to its maximum. So they are indicative diodes. And these little capacitors are shunting capacitors in positive and negative branch in which voltage is controlled. They are 10 microfarads and 450 volts each. And here is a diode bridge which I use as rectifier. It is divided into two parts and serves as a rectifier in each branch. And here is the place for capacitors which are under charge. There are only two cascades now. The first is 4 capacitors, each 550 volts and 450 volts and 470 microfarads. So two such capacitors in each branch. And the second cascade is 470 microfarads and 220 microfarads. There are also neon lamps in each cascade. Here is also a vast place for another cascades, which I will charge later. And my voltage tester is connected across all the circuit to the positive and negative point, so it should be 900 volts when it is fully charged. Okay, let's begin. Here is linear voltage regulator, which works from the rectified 12 volts and supplies all the circuit with stabilized voltage. Okay, let us start charging. Yes, we can see that the optorelays are closed, they are activated with the operational amplifier, and these diodes show that they are in work. And the voltage is increasing, 600 volts. Our neon lamps also are ignited. Okay, voltage builds up not very quickly because the capacitors are old. They more than a month I didn't use them, so I think leakage currents are high enough. And also maybe I should decrease these ballast capacitors. Maybe I should use twice less of them. Okay, now we are near our aim. Okay, one of the branches is near its threshold. Yes, you see that the optopair begins blinking. The voltage is close to 900. Now we will, okay, yes, this diode lights up, and now this yellow, okay. So both branches are charged. It is 900 volts. Okay, that's all. Maybe this circuit will be helpful for somebody.